Hello, everybody. In this video, I'm going to talk about the Jordan forms. This is for the course of linear algebra at the University of New South Wales. The course is in the second year, Maths 2099, Maths 2501, means are the courses, the name of the courses at the University of New South Wales. And part of the reason is just to help to my students by solving some questions, examples. So Jordan forms any matrix. So we learned that the matrix diagonalizable. It is very nice because we will be able to take the power of that matrix. With any power, it will be much more easier if it's a diagonalizable because we will be able to multiply only three matrices for any power. And a similar idea lead us to what if any matrix is similar to it? Can we sort of categorize them? Can we classify them to understand them? How we can approach? So if you have any n by n matrices, it is similar to one of the Jordan forms. And we will explain what are the Jordan blocks. These are the blocks of the things. And we have the direct sums. These are the direct sums, as we explained in the lectures. And the lambda 1, lambda 2, lambda k's are the distinct eigenvalues. And if you add those blocks, ended up will be the same dimension as you started with your n matrix n. Now let's do the example and explain on the example. You have let's do the 2 by 2, which is simple, but the subject to understand it is will help to solve the other dimensions. It is sometimes it's easy to understand in the small dimensions and to extend that idea in the higher dimensions. So we would like to show three things in this question. We would like to show that A is not diagonalizable, and we will find out the generalized eigenspaces, and we will find the matrix A as a multiple of an invertible matrix P and the Jordan form PJP inverse. So that's the format that we would like to find. And we find a basis consisted of the chain of the generalized eigenvectors, which give us this decomposition. That's the general idea for the Jordan forms. It's always the case. Okay, first we would like to, for the not diagonalizable, we would like to find out the eigenvalues and eigenvectors. Eigenvalues are the roots of the characteristic polynomial, and the characteristic polynomial is the determinant minus lambda I. And so A minus lambda I will be the only the diagonal one, so will be affected minus lambda because this is the identity matrix. Then we find this times this minus this times this will give you this, and then open it up this polynomial. Then we have 7 minus lambda minus 7 squared will give us this polynomial. So 7 is a root of this polynomial with multiplicity 2 because you have two here. These two, we call it the algebraic multiplicity. 7 is an eigenvalue with algebraic multiplicity 2. So then we will need to find out that the eigenvectors. So that's the eigenspace. 7 eigenspace, if we denote by E7, kernel of A minus I7 will be, we are detracting, or you just write it down, lambda is equal to 7 here, then we have 3 here, then we have minus 3 here. We have 3, we have minus 3. So we would like to find out what is the basis of this kernel space. And this is, if you multiply this row and add this row, then you will find the second row is 0. The first row will give you 3x is equal to minus y. And if you put y as some lambda, then you will have, or if you say x is equal to something, if x is equal to lambda, then you will find that the root is 1 over minus 3y will be the basis for this kernel space. Now we have one element here, one basis element. We found dimension 1. So the dimension of this kernel space is 1. So that is the definition of the geometric multiplicity. What we found, algebraic multiplicity is 2 and the geometric multiplicity is 1. If algebraic multiplicity and geometric multiplicity are not the same, that was the criteria for diagonalization. It is not diagonalizable at all. So in this, if it is a diagonalizable, then your Jordan form will be in this format because it is diagonalizable. If we find two basis vectors in this kernel space, everything would work out perfectly fine. Then we will have this Jordan form in this construct. We will have two basis vectors appearing here, which will give us the P matrix. But in now, we have only one ion vector here, one ion space. Well, the dimension of the ion space only 1. So we have one ion vector corresponding to 7, which is the ion value, but algebraic multiplicity 2. We needed 2, but we found 1. It means that the structure of the Jordan form needs to be in one block. We cannot separate them. We cannot find. So if this happens, if a matrix is not diagonalizable, then we need a extended version, generalized version of the ion space concept, because ion space concept is not good enough. We need to generalize it, to expand it. So that's the next. A here is a matrix PQ over the complex numbers because the complex numbers are algebraically closed. Every characteristic polynomial will have roots. So that's the only reason we have the complex vector spaces that we are thinking when we are doing the generalized ion spaces. You will not have the complex matrices, but characteristic polynomials of the characteristic polynomials of the matrices will be considered in the complex space. Okay, so this is just a convention assumption for you, nothing else. So generalized ion space for an ion value, for example, in this case, we need to think about it, right? So while lambda is equal to 7, we need to think about the generalized ion space because algebraic multiplicity is different from the geometric multiplicity, and we have this case. Okay, the definition of the generalized ion space will be the direct sum of the kernel of these operations. So a minus lambda I to the k. So this is the kth power, and then we are looking at the kernels of that one. And the k will be numbers like 1, 2, 3, and so on. Now, we call these ones we can denote these spaces, allow us to denote these spaces with y vk lambda for shortcut. And the dimension of these spaces are spatial, and they have some rules about these dimensions. So it's a combinatorial object. These dimensions, we call them a decay, even though depending on the lambda, if there's no confusion, we remove the lambda, we only denote by decay. If we are talking about only one ion value case, or focusing on one ion value. So this is the generalized ion space definition. And if you look at the sum over, okay, so you can think about all the powers. You're taking all the powers. But this space is not infinite. This sum will end up in somewhere. So the theory tells you that exists a theorem. It tells you that the sum is a finite. It means that it will stop in some stage. There will be an integer, at least high, h, for example, and then every term afterwards will be exactly the same dimension. So it stops in some stage, and that's one of the theorem says. And also there's another result which says that there is no pause. There exist some rules about these dimensions. It says that there's no pause, which means that this increasing order of these dimensions of these spaces cannot sort of grow, stop, and then grow again. That will not happen. So that's the no pause means. This will not happen. Now, this kernel space is actually, they include each other. They are subsets of each other. And this is generally what happens for any matrix, for any operation. If we have a kernel of that operation is a subset of the kernel of the square of that operation. So is also that space is a subspace of the kernel of the m's cube and so on. So this is a general fact, and we are going to use this fact in our work. This is basically in a graphic sort of schematic way to show it is kernel M will be the smallest set, and then the kernel M squared, and then the kernel M cube, and so on. Just I'm using this schematic expression just to show you how it works. Okay, let's calculate it. So so V1 will be exactly the same. It's because it's the first power, and we already calculated. So K is equal to 1 case is exactly the eigenspace that we started with. So D1 is the dimension of the eigenspace, which is 1 in our case. That's what we've done this calculation just before. Now we are looking at the square for K is equal to 2Ks. We would like to understand what is the square of this operation. A minus 7i squared. If you multiply this matrix by itself, you find a zero matrix. But the zero matrix, the kernel of the zero matrix will be the whole space, because whatever the vector you have here, you're multiplying with the zero matrix, you will always get the zero matrix. So this space contains every vector. So this space is a C2 already. That's what I am saying here. So everything afterwards always is C2. So the generalized vector space will be this one is our eigenspace, the E7, and this one is C2, and this one is C2, and you're summing up, but the C2 plus C2 plus C2 plus is always C2. So, and the V17 or E7 is inside the C2. So the generalized eigenspace for lambda is equal to 7 is C2. Then, so V2, dimension of V27, which is this guy, is C2, and that is dimension 2. And in some stages, always, since you have a 2 by 2 matrices, in some stage you will reach that. Okay, the diagram for this one will be D1 will be one-dimensional, and D2 is D2 minus D2 is 2, D2 minus D1 is 1. So 1, 1 is what we represents this is the geometrical. I will explain this one a lot better, but this is the geometrical, this is the combinatorial object related to with the dimensions of the generalized eigenspaces of the eigenvalue, and that's how we do. We start with the D1, we looked at the D2 minus D1 and so on. Okay, now the tutorial tells us that if you get a point here, a vector here in C2, so this is the kernel of degree for K is equal to 1, this is the kernel for K is equal to 2. And we choose a vector in this here, but not here, then we will be able to apply the A minus 7i operation we will be able to find another vector inside here. This is how it works. So if we choose a V2, which is linearly independent with the basis of V1, it means that we are choosing a vector here. Not here, but here. So mathematically, we say that this is choose V2 such that V2 is not in V1, but in C2. One of the natural choice, because C, the basis is 1 n minus 3. Any vector which is not multiple of 1 minus 3 will be a linearly independent vector. If I choose 1, 0, is linearly independent to 1 minus 3. But if I apply a minus 7i to this vector, I will be able to find a vector inside the ion space, not the generalized polynomial, it's the ion space when k is equal to 1. So this matrix times 1, 0 will give me a vector 3 minus 9. That will be 3 times 1 over minus 3. That is also an element in V1. So choose this vector, tell this vector is V1. So what we found here, from this equation, a minus 7iv2 is equal to V1, will be a V2 is equal to 7v2 plus V1. But since V1 is in here, it means that it is an ion vector of A. It means that A times V1 is equal to 7V1. So we have this equation, we have this equation. These two equations give us as a multiple of the matrices. So if you put this is the column vector V1, this is a column vector V2, and V1, V2. A times V1 as a matrix multiplication will give me V1, V7, which it will be the first equation. And the second equation, A times V2, is equal to this times this V1 plus 7V2, which will be the second equation. So these two equations is equivalent algebraically this matrix multiplication. Call this matrix P and call this matrix J, then we have AP is equal to PJ. But P is invertible because V1 and V2 are linearly independent together. If you have linearly independent column vectors, your matrix are invertible. So that's P is an invertible because the columns are linearly independent. If it is invertible, we can multiply from this side by P inverse. Then we obtain A is equal to PJP inverse. Now your calculation finishes here, but you can check it out what's exactly happened. So this is your P, and you can calculate the P inverse. The green part shows that the formula for the calculating the inverse of the 2 by 2 matrix. You can use this formula to calculate the P inverse. And if you do A times P and then P times J and figure it out that they are the same vectors, that will be the check-in point for you if you want to double check with your calculations and what's going on. So this is the 2 by 2 case. Now let's have a look what is the 3 by 3 matrix, Jordan form of a 3 by 3 matrix. This is another example. Now our matrix is A. Now we would like to find out ion values. So that is the determinant of the A minus lambda I, which is the characteristic polynomial. Calculating the determinant, whatever the determinant, how you calculate it, this times this, and that will give you 0. This times this will give +1. That one will give you 3 times 2 minus lambda. This one will give you 0. This one will give you 0. So eventually, if you work it out, the determinant of this matrix, you will find that lambda minus 3 is lambda minus 3 to the cube is the characteristic polynomial, which means that lambda minus lambda is equal to 3 is the eigenvalue with algebraic multiplicity 3. So that 3 here is algebraic multiplicity. Okay, now if you look at the eigenspace, which is the kernel of A minus 3i, just taking the 3 on the diagonal entries of the matrix will give you this matrix. And if you find, I'm missing out some calculations here, I'm just giving you the result. And it is pretty straightforward to calculate. If you calculate the register of echelon form of this matrix, will be the index form. And the last row says the the last row says that the z is a free variable, and second row says that the y is equal to z. First row says that x is equal to minus z. That will give you basis of minus 1, 1, 1, which is the vector that is a basis of the eigenspace E3. Basically, what we call this one is an eigenvector corresponding to eigenvalue. But we know that every vector here is an eigenvector. Now, since so the diagonal dimension of E3 of this space is 1, so the geometric multiplicity is 1. But the algebraic multiplicity is 3 and the geometric multiplicity is 1, it means that they are not equal. So A is not diagonalizable. Since A is not diagonalizable, Jordan form cannot be this, right? You cannot have 3, 3, 3 on the diagonal. That is not the case for this one. So you cannot have the Jordan form 3, 3, 3, 3 on the diagonal, and the 0 is elsewhere. That cannot be J. That cannot be our J anymore, right? So that is impossible for us. And so we have two possibilities. We might have 2 by 2 block and one here, or we might have a 3 by 3 block. We might have this situation or we might have this situation. So in order to be able to see that, we need to calculate the generalized eigenvalues. For the k is equal to 2, for level 2, we need to look at a minus 3i square. So if we take the square of this matrix, a minus 3i, we find this matrix. If we take for the k is equal to 3k's, we need to take the third power. If you take another multiply this matrix with this matrix again, we will find a 0 matrix. So it means that a kernel of a minus 3i cube is the c cube. Right? Again, in our mind is this fact that the kernel M is inside the kernel M square, kernel M cube. So that's a kind of a situation we have. It's inside the inside. Since the largest one is a C cube, all of those ones, like C cube contains all the others. So the generalized eigenspace of lambda is equal to 3 will be just as C3. So the next, we would like to find out, these are the other notes, so I'll just clean it up. Okay, so find a basis, we would like to find a basis of consist of one or more chains of the generalized eigenvectors so that we can construct the Jordan form, understand the Jordan form, and the P matrix, right? These chains will give us the P matrix as we've done before. So, okay, so this square case, for k is equal to 2k's, we are looking at we need to calculate the basis of this vector space, V3. So that's the kernel space. And we take the square as we calculate this one before, which was this matrix, and which is that one. So we would like to calculate the kernel of this matrix. It is pretty straightforward to see the reducer of echelon form. this row is equal to that row, and if you add this row to this row, then you will have 0, 0, 0 as well. So all these ones, y is an independent variable, z is an independent variable, and x is equal to y minus 2z. So we have two bases in this vector space. And one of them is 1, 1, 0, another one is minus 2, 0, 1. Okay, that's the level 2, and the dimension of this space is 2. So generalized for the chain of the generalized vectors, we would like to find out a vector in C3, which is the highest degree of the generalized eigenvectors, in C3, but not in V3. So that I pictured that here. We want the W to be here, but not in V2. So then we apply the operation. W in this case can be taken as 1, 0, 0 because 1, 0, 0 is linearly independent with these two vectors. Okay, and then we apply the operation A minus 3I to this vector. We found 2, 0, minus 1. And 2, 0, minus 2 will be in the V vector V2, and we exactly found this one. We could find a linear combination of these two, but for simplicity, luckily, we found a vector which is exactly one of the eigenvector, one of the basis vectors. Then this is called this vector u. Now we are in V2, which you're in here, that's u. Then you apply the transformation again, which is a minus 3I onto u. Then we found the vector 1 minus 1 minus 1. That is, if you look at the kernel of this one, see this is spanned by minus 1, 1, 1. And clearly this vector, it is just a minus of that vector, is inside the V3. We don't care about the minus or plus, or doesn't matter. But we call this one as a vector V because that's the end of the chain for us. What is important for us for V? V is in E3. So it satisfies the equation like A times V is equal to 3V. So this one is an important part to find in that. The chain ends. So these are the exactly things that we found. We took the W, we apply A minus 3I, we found U. We apply again A minus 3I, we found V. So that's what we found. So we found the full chain, and this chain is called the Jordam chain. Okay, now we can write it down, those equations, in a way that it will allow us to write it down, J matrix and a P matrix. So this equation is AW 3W plus V, AU is equal to 3U plus V. This implies this implies this implies this. Then, so AV is equal to 3V, which is that guy. AU is equal to V plus 3U, which is this equation, which is correct. So AW is equal to U times 1, 3 times W, which is the first one. So this equation exactly is the equations of like this. So they are exactly the same. So this is exactly, that gives you A times P, P times J equation. And here, D1 is equal to 2, D2 is equal to 2, D3 is equal to 3. And if you want to show it in terms of this combinatorial object with this graph, we call them Young tableaus. So that all corresponds to this kind of boxes. to express this Jordan block case. Okay, yeah, if you want to write it down, P in terms of the VW that what we've done, this is V, this is U, this is W, and you can figure out the P inverse and you can check your calculations. This is satisfied. Okay, now I would like to move on to a 4x4 case. Right, that's what I want to do. Now this is the 4x4 case. A is in this case, the A has eigenvalues 5 and 6 only. And we would like to find out the Jordan form and change the basis of P for A such that A is equal to PJ, P inverse. Okay, since 5 is the eigenvalue, then E5 we will eigenvalue with corresponding lambda is equal to 5 is the kernel of A minus 5I. So basically you're taking a 5 on the diagonals, 5, that will be 4, that will be 2, that will be 1, that will be minus 5. So that's what's on the diagonal. All the others are the same. If you find the reduced row echelon form of this matrix, you will find these 2 rows and all the other zeros. That will give you x3 and x4 will be free variables. The first row will give you x1 is equal to x4. The second row will give you x2 is equal to x3 plus 2x4. It means that you have this vector, and this vector will be the basis of this space. So that's what I'm saying here. So there's a span by 0, 1, 1, 0, 1, 2, 0, 1. And the geometric multiplicity will be 2, right? Because we have the 2 basis vectors that we found. The geometric multiplicity for 5 is 2. Now have a look at the geometric multiplicity of 6. And then by taking away 6 on the diagonal entries, we will have this matrix. Reduce this matrix, we find this matrix, and this matrix means that the last row shows that we have 1 free variable, then all the others are determinant with respect to that. It means that the dimension is 1, and it is easy to figure out that the basis of this vector space 1, 2, minus 1, 1. And the geometric multiplicity will be 1. So how we figure out the other eigenvalues, because we only know 2 eigenvalues, which is 1, 5, and 6 are given, and we don't know the other. So what we have here is the trace of the, very important, trace of the A is equal to the sum of the eigenvalues. This is a theorem tells us. By using this fact, the kernel, if you add 9 plus 7 plus 6, will give us 22. And now we have a sum multiple of 5 and sum multiple of 6. So algebraic multiplicity is always the highest. So geometric multiplicity is always smaller than equal to algebraic multiplicity. So since we found the geometric multiplicity 2 for 5, so the A will be either 1 or 2. And we found the geometric multiplicity 1, and the B can be only 1 or 2. But then we will have A times 5 and B times 6. So this means that A has to be 2 and B has to be 2. So algebraic multiplicity of 5 is 2, perfectly fits. And the algebraic multiplicity of 6 needs to be 2 as well. That's how it works. I mean, otherwise the equations will not be solved. That will be 10 here. Then it will be 12. And what is the multiple of 12? What is the multiple of 6 will give you 12. B has to be 2, right? So algebraically, you will find algebraic multiplicity is 6 by using the equation, by using the fact that the trace of the matrix is equal to sum of all eigenvalues. Okay. Now, since algebraic multiplicity is, and the geometric multiplicity is 2 for the lambda is equal to 5 case, is a kind of a diagonalizable in the small block for 5, corresponding to 5. It is not the whole thing, but the corresponding to eigenvalue lambda is equal to 5, this is a diagonalizable form. So what I mean by that, the Jordam form here will be 5, 5. There will be no 1 because algebraic multiplicity is equal to geometric multiplicity. So I have one block and one block. That implies this. Because I have enough number of the eigenvectors coming from the eigenspace corresponding to eigenvalue 5. I have two eigenvectors. Yeah. And algebraic multiplicity and geometric multiplicity is 2. I have enough 2 column vectors to plug in the matrix P in my calculation, corresponding to eigenvalue lambda is equal to 5, lambda is equal to 5, which appear twice in the Jordam block decomposition. Okay, for the other eigenvalue for lambda is equal to 6 is a little bit different because algebraic multiplicity is 2, but the geometric multiplicity 1. So I don't have enough vectors. I don't have enough basis vectors, which will give me the enough column vectors for the constructions of the matrix P. I need then the generalized version of the eigenvector. Then I need to calculate the generalized eigenspace for the eigenvalue lambda is equal to 6. I need to calculate a minus 6 I square and calculate the kernel of that space. If you calculate the a minus 6i square as an operation, as a matrix, you will find this matrix and then calculate the kernel. You need to reduce row echelon, find the reduced row echelon form of this matrix, which give you something like this. And this matrix tells me that y and x3 and x4 are the free variables. Then I have 2 bases. I will obtain the 2 basis vectors from this space. And these are the basis vectors coming from these equations. It is easy to figure out. So what I found here, E6 is consists of 1 vector, and V26 consists of 2 vectors. And that is the generalized eigenspace for E6. Now, if we're going to choose a vector here, but not vector here, we only need a chain over 2 because we have 2 vectors, 2 column vectors for corresponding the lambda is equal to 5 eigenvalue. Now we need 2 eigenvectors correspond 2 basis vectors corresponding to lambda is equal to 6, 1. So we are going to work out a vector. We will take a vector in this space, but not in this space. And then we will find a chain in order to be able to use that chain to construct the P matrix. Okay, so this vector is already in here, but not here. We can use this one and apply the a minus 6i to this vector. We will obtain this vector, call this one u, but this vector is absolutely minus 1 multiple of this basis vector, which means that this vector is inside here. That's what we wanted to find out. We choose a vector here, apply, and the transformation in this case will be a minus 6i. We want to obtain a vector in here, in E6. That's what we found, right? With W gave us U. So basically, this equation means a minus 6iw is equal to U, and U is in 6 means a U is equal to 6U. And these two equations gives us A times U is 6U, yeah, that's what it is as a matrix multiplication. A times W will be U plus a 6W, which is the first equation, which is this equation. So these two equations gives me this matrix multiplication. And here I have only the corner. I mean, this A is not complete A. It is A. Pardon, sorry. Okay, that's A. But I'm talking about, I mean, the dimension is not correct here. To fill it out, this space with the zeros. Right? They make it a 2 by 2 as a block. Right? So what I'm saying here, I've done a little bit of quick work here. That should be like a block of the zeros here, and then you have a block of 1 here. That's how it fixed. Okay, and I think I need to add the zeros as well, right? For this case. So this is not explicit, so this is why I am saying we are thinking of like that. It is not an explicit mathematical equation here, but it is like that. It is this corner here, and then I have these are first two are coming from the basis of the E5, and these two is coming from this is U and this is W, which are coming from here. And dimensionally, this is not explicitly to say it, but this is how we are thinking to get these two. Now, as multiplications of the matrices, A is equal to Sj S inverse is the Jordan decomposition of the matrix A. I think that is clear what I'm trying to say. Yeah, don't write this one, but it's just to think about it. Yeah. This is how we think about it as it is. Since we have the dimensions are 4 by 4, we are not really 2 by 2, but we are looking at the subblocks, and the subblocks is like a block case. And this is the right way to write it down. So this is the J matrix, and this is the S matrix, and this is U, and this is W, and these are the two basis vectors corresponding 5. You cannot interchange these two, but you can interchange these two, because if you interchange these two, this one will remove here, right? The appearances will be different. So appearances is explicit for this chain, but you can swap these two columns because both of them are basis vectors of ion vector corresponding to ion value lambda is equal to 5. I think that is clear for what I mean by that. Okay, now I would like to move on to this decomposition thing. I would like to talk about a little bit of this combinatorial object. And only the looking at the D's will make a lot of differences for us. It makes it very easy. If you have a really, really large Jordan forms by just looking at these rules on dimensions of the generalized spaces, we will be able to work out so much information about the Jordan forms of the matrix. So this is what's all about. So for example, if you have a matrix 9 by 9 matrix and has only one ion value, lambda is equal to 3, and a lambda the nullity of in the first degree is 3. So this means that D1 is equal to 3. And the nullity of a minus 3i squared is 5. This means that du is equal to 5. In this question, we would like to find all possible Jordan forms. If a is ever given, what would be the calculation we need to know to determine the Jordan forms? Okay, now since we have a 9 by 9 matrix and nullity of the whole matrix and is the kernel dimension of the kernel space of this matrix, as we know. So D1 is equal to 3, D2 is equal to 5. It means that we have 3 boxes. We put 3 boxes on the down and 2 boxes on the bottom, on the up. And then we have left with the 4 boxes. And each of those boxes are replaced. I think, just give me a second. I wanted to. I'm just looking for the place that I replaced these, the explanations of these. Okay, the dimensions have the rules. These rules are, they are increasing order. They are always increasing order. And the differences between them gives us something on the block. So I really need to explain this. Okay. So in general, you always have D1. You have to start with the D0, and this is D0 is always 0. And then you have D1. These are the dimensions of the always. Yes, this is the nullity and decays. Decays are the nullity of the kernel space of the matrix minus lambda I to the power k. That's the dimension of it, or nullity of a minus lambda I to the k. And you have dimensions here, and in some stage it has to finish. But see, if you have only one eigenvalue, then it has to be, some stage it will finish, and it will be smaller than equal to dimension of the vector space. But if you have an n by n matrix, if you have a one eigenvalue, this should end with n, right? But in general, it's a smaller than n, but it will be n if you have only one eigenvector. And if you look at d1 minus d0 and d2 minus d1, these were always will be increasing and it will never stop. Right, that's what the theory says. This is what the no pause implies to. So these are the rules for the dimensions of those spaces. So when each of these spaces, we denote number of the boxes we put it here with d1 minus d0, which is exactly d1. And then you put number of the boxes on the top, which is equal to d2 minus d1, and so on. And then eventually you will have some number of the boxes here, what these boxes says is what these rules represents. These boxes cannot be larger than the previous one. It has to be either equal or smaller. It can be like this, or it can be smaller than this, right? It can, that's what it is. So D2 minus D1 can be smaller, 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 smaller. And in some stage it finish, maybe it will finish in one rows. And this will give you the exactly the Jordam number of the Jordam blocks that you have. How you do that? Now, we looked at, once we construct all of those, and in the end of them, of course, you will have dh minus dh minus 1, whatever that number is. Could be 1, could be 2, depending on how this letter looks at. There's a explicit letter. And then we looked at the number of the boxes on each column. Let's say this one is k, and then you will have jk lambda in the one block. And then we looked at the other one, maybe it is a M block here. Then we sum with the JK, JM lambda. So these ones is the dimensions of the Jordam block, and this one is that gives you the dimensions of the Jordam block. These are the combinatorial way to look at the dimensions and looks at the rules of the dimensions. That's how it works. So this is the example related with this idea. Okay, now in this case, D1 is 3. Right? D1 is 3, D2 is 5. Now you have 3 blocks here. D2 minus D1 will be 2, so this is why you have 2 blocks. See, you have a ladder conditions here. Now, since I have 9 dimensions, I have a 9 by 9 equations, matrix, sorry, and then I already used 5 of these equations, 5 of these boxes. I left with the 4 boxes behind. So all these constructions, possible constructions based on this structure, I can put all these 4 boxes with this fashion, right? On 2 by 2. That is the one way to do it. I'm going to look at all the possible ways that I will put 4 boxes on the top of this construction such that it will be in the ladder way, right? So if I put 2 boxes here, I can put 2 boxes or one boxes here. So this is one of the possibility for 4 boxes to configure of these 4 boxes, how it appears. And if I put the 2 boxes here, I also can 1 box here, 1 box here, that is possible. Or on the 4 boxes, if I put 1 box here, I have to put 1, 1, 1 boxes because the ladder cannot exceed 1 before, right? And it means that all these differences is getting smaller and decreasing, or they're getting smaller and smaller. It means that the ladder cannot exceed to that box number of the boxes. These are the rules for the dimension. So these are the 3 possibilities that may happen in this case. If D1 is 3, D2 is 5, and A is a 9 by 9 matrix, these are the 3 possibilities may happen. If this happens, then we have 4 blocks in the first one, 4 blocks in the second. So I have J4, 3, and J4, 3, and then this one J1, 3. So this is the Jordam form corresponding this combinatorial object. For this one, I have 1, 2, 3, 4, 5. 5 in the first column, so that is 5, Z5, 3 block. And I have 3 blocks here, Z3, J3, 3 block. And I have 1 block here, so that's J1, 3 block. For this possibility, I have 1, 2, 3, 4, 5, 6. I have 6, J6, 3. And I have J2, 3, and J1, 3. So For this one, we can figure out the dimensions with respect to the configuration, right? If this is the case, then D7 has to be D3 needs to be 7-dimension because I'm putting the 2 blocks in here. So 5 plus 2, the difference is 2. So this is why it has to be 7. And since I put the 2 blocks in here, then I add 2 blocks. So D4 has to be 9-dimensional. So these are the possibilities. So 3, 5, 7, 9, that is the D1, D2, D3, D4. That's the possibility corresponding this configuration. For this configuration, we put 2 blocks in here, so the D3 has to be 7. We put 1 block here, D4 is 8, and 1 block here, D5 is 8. So I have 3, 5, 7, 8, 9 is the construction of the Ds. For this one, we always add 1 block, 1 block, 1 block, so the dimension increases only 1 block in each step. So I have D1 is 3, D2 is 5, D3 is 6, D4, right? 1, 2, 3, D4 is 7, D5 is 8, D6 is 9. So I have this decomposition for ion spaces. Right, these are the dimension Ds. These are the Ds. Okay, what else we need to know? Well, for this case, if we know this D3 is equal to 6, if this is 6, then it means that only one possibility, everything should go up, 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 up. That's the possibility 3. If you know this one is 6, D3 is 6, that's the only possibility because you to go down to one level, every letter has to be 1, 1, 1, no other options. But if D3 is 7, we have these 2 options. Then we need to look at D4 in order to be able to figure out how it works. So if D4 is 8, then we have possibility 2. And if D4 is 9, we have a possibility of the first possibility. Yeah. Okay, let's do more exercise. If we have 14 by 14 matrices with one ion value, let's say lambda is equal to -2, D1 is 4, D2 is 8, D3 is 11. What other possibilities may happen? So the first one will be, we will have 4. From here to here, we have 4 blocks, so we have 4 blocks in here. And from here to here, we have 3 blocks. We have 3 blocks. What is left from 14 minus 11, we have 3 blocks. So we have 3 blocks to put on the top of this structure here. We can put 1 block each of up. We can put 2 blocks and 1 block up, or we can put 3 block as it is because that's the maximum that we can have. And for this case, we have 1, 2, 3, 4, 5, 6. 6 for the first one, so that's J6. Then we have J3, J3, J2. These are the ones that we have. And if we have this situation, we have 1, 2, 3, 4, 5. J5 for the first block. J4 is the second. J3 is that one. And J2 is this one. For this possibility, we have 1, 2, 3, 4. 4, 3 times appears J4 minus 2, J4 minus 2, J4 minus 2. And the last one is J2 minus 2. So these are all possibilities for this one. If I have 12 by 12 matrix and k is equal to 1, I have 4. K is equal to 2, I have 6 for the dimensions. And what will happen for the ion value 7? And this one for the eigenvalue 3 for -3, I have k is equal to 1 is 2, k is equal to 2 is 4, k is equal to 3 is 5. These are the decays. And what is the possibility? What is the solution of this? Well, lambda is equal to 7. It means I have 4 possibilities here and 2 possibilities here. For lambda is equal to 7, I have J2, J2, J1, J1. So that's the Jordam form. And for this part, for lambda is equal to -3, I have 2 and 4. And 2, 4 minus 2 will be 2 blocks on the top, and the 5 is the 50 here. So I will have 3 and 2 and 1. So sorry, this should be 3 here. So 4, 5. Okay. So I have 2 plus 2 plus 1, 1. I have 3, 2, 1. I think that's what it is. So I have a 5 here, 5 here, 12 here. In this case, it's just really 12, and it finishes off the whole possibilities. That's what it is. So if this is the case, that's 2, that's 4, that's 5. Yeah, that's all finishes because it is really 5. I think that's an error here in other possibilities. That should end here. If this is what's happening. This is 4 here, that's 6 here. That's 2, 4, 5. Right? That's 3 and 2. There's no 1 here. This is 3, 2, 1. And then you will have you will find 11 on this side. So you must have 1 block. So x is equal to 1. Then you will have 1 block needs to be added here. You can add here or you can add here. It can be here or it can be here with respect to 2 possibilities. You have 2 options for that one. That's what I mean by that. You can add here for the 7, you can add here for 3, and J forms will be either this or this. Okay, I think I will get that one. Okay. And this one is other way around. Okay, let me say this one is the last thing that I would like to say about this. You are reading other way around. So another type, another versions of the dimensions of the Jordam forms, the compositions of the Jordam forms, can be asked in this question as well. So for example, if the Jordam form is given, now we would like to find out what is the size of what is the dimensions of the matrix, and what is the nullity of these operations, a minus lambda I to the k. So for every eigenvalue lambda. So the first question is given by this Jordam form. J is equal to 6 is the one eigenvalue. Now, if you add these yellow ones directly, it will give you the size of A. So you have 3, 2, 1, 1, 1. It is 8. So that you have size 8. So this means that you have a 3 by 3 blocks, you have 2 by 2 blocks, and you have 1, 6, 6, 6 blocks here. So it's a dimension of 8. So you don't need to do this, but I just would like to show that this is the case. So if we do that, how we can go back to the case? So what we were doing previously, we were writing the D1s and then looking at the D1 minus D2 and constructing row by row and then reading column by column. So we will do the other way around this time. So when we say 3, you put the 3 columns on the diagonal. That's the first thing that we are doing. And then the 2 blocks over here, and then the 1 block, 1 block, 1 block. You're constructing with the vertical way, the boxes the vertical way, and then calculate the differences, and that will give you the dimensions. So the first one is D1, and the second one, D1 plus 2, will give you the D2, and then the D2 plus 1 will give you D3. And that's exactly other way around what we were doing in the previous work. We were working out with the row by row and then reading column by column. If you know the Jordam form, you need to construct your combinatorial object, which is the Young tableau, column by column, and read row by row. It is natural. So for example, this one, you have 4 plus 4 plus 4 plus 2 plus 2 plus 2 will give you the dimension. So you have 1, 2, 3, 3 4s, you have 3 2s, will give you 18. So the matrix size will be 18. And then in order to be able to construct this with respect to and find out the D's, the dimensions of the each direct summand of the generalized eigenspaces will be the first one is 4, the second one is 4, third one is 4, and then 2, 2, 2. So this one will be 4, and this one will be 8, this one will be 12, and 2, and 2, and 2. So that's how it works. You will find out all D's in that way. And similarly, you can figure out all the others. If you have this kind of Jordam form with the different lambdas this time, you need to look at the different lambdas in their own corner. You will have different Young tableaus for corresponding different eigenvalues. So for lambda is equal to 2, you will think about this one, this one, this one. So you have 3. You have 3, 3, 1. That will give you D1 is 3, D2 is 5, D2 is D3 is 7. That's the case. And for this one, you have 2, 2. This is the simplest one. It is 2 in both direction. So you have D2 is 4. And 4 is equal to 2. It means that you have one long vertical one because everything 1, 1, 1, 1. That gives you J4. For D1, it increases. D1 is 1, D2 is 2, D3 is 3, D4 is 4 for that eigenvalue. So here, this kind of the dimensions of those kernel spaces corresponds A minus lambda I to the power of K dimensions. The Ks have combinatorial properties, and this kind of questions in both directions can be asked as well. I think this covers everything about the Jordam forms, and hopefully it is helpful for everyone. Thank you very much for watching.